Let us begin a question-answer session of mathematical physics with this lecture. So this is lecture number 1 and we would address some questions that were asked in various competitive examinations. The first question coming up. Consider two matrices A and B. Define the relation AB minus BA as AB within third bracket, and this is called the commutator bracket. Again, the relation AB plus BA is written as AB within second bracket or the curly bracket, and this is called the anticommutator bracket. If the anticommutator bracket is 0, then show that the commutator bracket of A and BC is negative of B into the anticommutator bracket of A and C. The answer: given the anticommutator bracket of A and B is 0, which means AB plus BA is 0. This means that AB equal to minus BA. Now let us expand the commutator bracket of A and BC. It is A into BC minus BC into A. Let's write it straight as ABC minus BCA. Now AB is minus BA, so this is equal to minus BAC minus BCA. Note that minus B occurs in both terms, so we take minus B common and the leftover portion is AC plus CA. This portion is the anticommutator of A and C. So the commutator bracket of A and BC is equal to minus B into anticommutator of A and C as wanted. Next question. Find the trace of e to the power A, where A is a 4 by 4 matrix, and let us write it. First row is 0, 0, 0, pi by 4. Second row is 0, 0, minus pi by 4 and 0. Third row is 0, pi by 4, 0, 0, and comes the last row. It is minus pi by 4, 0, 0, 0. The answer. What is trace? What do you mean by trace? Trace is the sum of the diagonal elements of a matrix. Let us use the well-known relation of exponential series, namely e to the power x. E to the power x is equal to summation over 0 to infinity x to the power n divided by factorial n. And let us expand this summation. So e to the power x is equal to x to the power 0 by 0 factorial plus x to the power 1 divided by 1 factorial plus x square by 2 factorial plus x cubed by 3 factorial plus x to the power 4 by 4 factorial, and the series continues to infinity. Let us rewrite the series in the popular way. We write it as we use the same formula to write e to the power A, which is, let us note that A is a matrix, a 4 by 4 matrix to be particular, and so the first term is actually a unit matrix, of course 4 by 4, and let us denote it by the symbol capital I. Clearly we have now to evaluate A square, A cube, A to the power 4, A to the power 5, A to the power 6 and so on, and we do it now. It will not be hard as it seems at first sight. Rather, it would be easy. Let us see. This is matrix A. Take the factor of pi by 4 common and we are left with 0, 0, 0, 1 as the first row, 0, 0, minus 1, 0 as the second row, 0, 1, 0, 0, this is the third row, and the fourth row is minus 1, 0, 0, 0. What is A square? It is A into A. So we have to first write the A matrix twice, and let us write it. And then multiply Matrix multiplication is term by term multiplication of a row of the left matrix with the column of the right matrix and then adding. So what we get is pi by 4 whole square as it occurs twice, and the product matrix, which is what we end up with is a square equal to minus pi by 4 whole square into the unit matrix I. This, you would agree, is a simple result. Let us find a cube. Split it as a square into a, put the value of a square, and the result for a cube is minus pi by 4 whole square into a. Now a to the power 4, it is a cube into a. Put the value of a cube, which is into a. This generates a square, the value of which is, so the final answer for a to the power 4 is, now a to the power 5, which is a to the power 4 into a, and putting the value of a to the power 4, we get a to the power 5 to be, a to the power 6 can be obtained similarly from a to the power 5 and then using a square. And similarly we get other powers of a. Now we turn our attention to e to the power a. It is let us collect the results for various powers of a, for instance a square, a cube, etc., and write them down at one place. They are needed to write down the expression of e to the power a. Put this for a square. We substitute for a cube. This is for a to the power 4, and for a to the power 5 we have, and this one for a to the power 6, and so on so forth. The series extends indefinitely, that is up to infinity. It does not end. Let us simplify a bit to get now let us find trace of e to the power a. First term is trace of I, second is trace of a, third term involves trace of I, fourth term involves trace of a, fifth term contains trace of I, sixth term has trace of a, while the seventh term involves trace of I, and so on up to infinity. Use trace I, that is trace of this 4 cross 4 unit matrix, which is 1 plus 1 plus 1 plus 1 equal to 4. Also trace of A is trace of this matrix, which is 0 plus 0 plus 0 plus 0 equal to 0. Let us rewrite the expression of trace of e to the power a that we have derived, and it is now put trace of I equal to 4 at these places and trace of a equal to 0 here at these places. So trace of e to the power a simplifies to, let us take 4 common and we are left with, use the fact that cos of x can be expanded into an infinite series as, here x is pi by 4. So trace of e to the power a is 4 cos pi by 4. Put the value of cos pi by 4 to be 1 by root 2. This gives, on simplification, 2 root 2, which is the answer. Let us move over to the next question. Evaluate the integration from 0 to infinity dx x to the power 9 e to the power minus x square. The answer: consider the given integration. Now put x square equal to xi. So we make a change of variable from x to xi. This means x is xi to the power half. It also leads to 2x dx equal to d xi. The limit of x was 0 to infinity, and that of xi, which is x square, will also be 0 to infinity. And dx is d xi by 2x, which is. So the integration is now an integration over the variable xi. That simplifies to. Let us use the standard integration that we would deal with in a future video, the result of which is factorial n, and this holds for n equal to 0, 1, 2, 3, etc. That is for positive integers. With this we have the answer to be 12. Next question. Consider the function f of x equal to x into e to the power minus x by lambda. Find where the symbol denotes average value of x and xp is the most probable value of x. Given lambda is greater than 0, a very important and decisive condition we shall see, and x ranges from 0 to infinity. The answer: given a function f of x equal to, obviously it varies with x. Average or mean value of x is given by integration over the range 0 to infinity x into f of x dx divided by integration from 0 to infinity f of x dx. This is the definition of average of x in the function f of x. Put the value of f of x and rewrite the right hand side. Simplify to get. Now make a change of variable from x to something else, say xi. So x equal to lambda into xi and dx equal to lambda d xi. Since range of x is 0 to infinity, the range of xi will also be 0 to infinity. So we write average of x in terms of xi, and we get lambda cancels out and 1 lambda is left in the numerator. So we have two integrations and we would write their value directly using the standard integration. So the answer we arrive at is 2 lambda. To get the most probable value of x, that is, at what value of x is f of x maximum. Maximum means f of x would show a peak. As the name maximum implies, we have to maximize f of x with respect to x. What are the conditions of maxima of a function? The first derivative should be 0. This is one condition. Let us check it now. Keeping in mind that if first derivative is 0, f of x can be either a maximum or a minimum too. So set df dx equal to 0. Put f of x and split into two terms, which gives clearly the product of two terms is 0. That means either minus x by lambda plus 1 is 0, or it may be that e to the power minus x by lambda is 0. Which to accept? Let us find what this leads to. It leads to a value of x equal to lambda, and this option leads to x equal to infinity. Why? As e to the power minus infinity is 0. Should we accept this result? Let's argue. At x equal to 0, f of x is 0, and at x equal to infinity, f of x is also 0. So f of x is 0 both at x equal to 0 as well as at infinity. What does this lead to? F of x is not 0 everywhere, but becomes maximum, so to say, lifts its head up somewhere in between 0 and infinity. In other words, the most probable value, that is maxima of f of x, lies somewhere in between. So f of x is not maximized at x equal to 0 or infinity, but at an intermediate value of x between 0 and infinity. Clearly, we cannot accept x equal to infinity as a maxima of f of x. We thus accept x equal to lambda. But is f of x maximum here or minimum? To be sure about it, we have to find the second derivative, d2 dx square of f of x equal to d2 dx square of, put the value of f of x, we split the derivative, and the first derivative we already calculated a few minutes ago gives. So we are left with d dx of, this gives, let us split this into two terms. Therefore, d2 dx square, that is double derivative of f of x, gives. Now at x equal to lambda, its value is, put lambda for x and we have minus 1 by lambda into e to the power minus 1. Let us use lambda greater than 0, that is positive, that is lambda is positive, which was the given condition, and this ensures that second derivative is negative. So we have shown that at x equal to lambda, first derivative is 0 and second derivative is negative. The condition of maxima is thus obeyed. So we now are assured that xp is lambda. Therefore, mean of x divided by xp is 2 lambda divided by lambda. The answer is thus 2. Next question. Solve for x if log of x plus 1 equal to log x plus 1. The answer. Given log x plus 1 equal to log x plus 1. Let us bring log x to the left side. This gives log of x plus 1 by x equal to 1, or log to the base 10 x plus 1 by x equal to 1. This means 10 to the power 1 is x plus 1 by x. This implies 10x equal to x plus 1, so x is 1 by 9. The answer. Next question. What is arithmetico-geometric progression or series? What is its sum? The answer. Arithmetico-geometric progression or series, let's abbreviate as AGP. Let's define it. Consider arithmetic progression abbreviated as AP. First term is say A, second term is A plus D. We shall set D as the difference between the terms. So the third term is A plus 2D, then A plus 3D, and the series continues in this fashion in a disciplined way up to the nth term. A, as we stated, is the first term and D is referred to as the common difference. This A is the first term, n equal to 1, and we can write it as A plus 1 minus 1 into D. The second term, that is the n equal to 2 term, can be recast as A plus 2 minus 1 into D. The third term is n equal to 3 and can be written as A plus 3 minus 1 into D. N equal to 4 is A plus 4 minus 1 into D, and so on. And so the nth term is A plus n minus 1 into D. Consider geometric progression or series abbreviated as GP. It is 1 plus r square plus r cubed and so on up to nth term. This is the first term 1 and this is the second term r, and second term by first term is r divided by 1, which is r, called common ratio. The first term is n equal to 1 and we can write it as r to the power 1 minus 1. Second term n equal to 2 is r to the power 2 minus 1. The third n equal to 3 term is r to the power 3 minus 1. Fourth is r to the power 4 minus 1, and so on. Hence, the nth term is r to the power n minus 1. Let us write the arithmetic series up to nth term. And this is the geometric series up to the nth term. Term by term multiplication of arithmetic series and geometric series leads to the arithmetico-geometric series. AP, the arithmetic progression, is of n terms. Geometric progression GP is also of n terms. We shall write it. Let the sum be Sn. It is a into 1, the n equal to 1 term, plus a plus d into r, the n equal to 2 term, plus a plus 2d into r square, which is the n equal to 3 term, and so on. This is the n minus 1th term, and this is the nth term. Let us rewrite the series, denote the sum up to n terms by Sn. Now multiply this series by r, the common ratio of the involved geometric progression. So we have r into Sn, and place the terms with a shift of one place beneath the corresponding term of the series denoted by Sn. So put a into r beneath a plus d into r, and so on. This is the n minus 1 term, and this is the nth term. Subtract to get 1 minus r into Sn equal to ar and ar cancel out. We thus are left with dr. Ar square and ar square cancel out, and we are left with dr square. The series continues, and we have the penultimate term as d into r to the power n minus 1, and put the last term. Note, due to multiplication by r, it is r to the power n. Take dr common, and a geometric progression GP results. The sum of which is 1 minus r to the power n divided by 1 minus r. This is because the first term is 1 and the common ratio is r. We thus have let us extend this series to infinity. So put n equal to infinity. As mod of r is less than 1, it follows that r to the power n, that is r to the power infinity, is 0. And let us replace Sn by s for convenience. We thus have s equal to a by 1 minus r plus d into r divided by 1 minus r whole square. This is the formula for sum of infinite arithmetico-geometric progression. Let us write it. Now it goes to infinity. Having derived the formula, let us move over to the next question. Find 1 plus 4 by 5 plus 7 by 5 square plus 10 by 5 cube, and so on. The answer. We code the series. This is an arithmetico-geometric progression. Since we find an arithmetic progression in the sequence 4, 7, 10, and so on, the common difference being 3, and a geometric progression is there too, namely 1, 1 by 5, 1 by 5 square, 1 by 5 cube, and so on. The common ratio being 1 by 5. Multiply by 1 by 5 to get, of course, placing the terms with a shift of one place. So place 1 by 5 beneath 4 by 5, and so on. And then subtract to get. We have got an infinite series, the sum of which is, it is 5 by 4 on simplification. Put it back to get S equal to 35 by 16. Alternately, we can derive the result of the sum of infinite arithmetico-geometric series by using the formula we derived. Let us rewrite the series and recast it as, clear that it is an arithmetico-geometric series, the sum of which is use A equal to 1, D equal to 3, R equal to 1 by 5 to get the sum to be 35 by 16. Next question, find 2 to the power 1/4 into 4 to the power 1 by 8 into 8 to the power 1 by 16 and so on. The answer, quote the quantity given, add the powers, take 1/4 common to end up with a series, and it is an infinite AGP, arithmetico-geometric progression. The sum of infinite AGP is here A equal to 1, D equal to 1 and R equal to half. So the answer we get is 2. Alternately, let us write it once again and construct the series, call it S. So S is equal to, now multiply S by half and write the terms with a shift of one place to match the corresponding terms of S. Take difference to get. Take 1/4 common and we end up with an infinite GP. So S is 1 and hence the given series is 2 to the power 1. So the answer is 2. Next question, find the sum of. The answer, let S be the given series. Multiply by 1 by 5. Why? Clear that the terms gradually are multiplied by a common ratio of 1/5. And we have to write the terms with a shift of one place. Then subtract to get a new series as, this is 4 by 5. Again we see that the common ratio is 1 by 5. So let us multiply by 1 by 5 to get. Write the terms with a shift of one place so that corresponding terms are in a vertical line. Then subtract and we get now we have clearly a geometric progression with common ratio 1 by 5, first term being 1. So the sum is, and this leads to the value of S to be. Next question, find 1 plus 2x plus 3x square plus 4x cubed for mod x less than 1. The answer, denote by S the series that has been supplied, which is an arithmetico-geometric progression. The terms differ by a multiplicative quantity, that is x. So we multiply by x and write the series again. We have x into S on the left hand side and the terms on the right hand side are written with a shift of one place to match the terms of the series denoted by S. Next subtract and we get 1 minus x into S equal to 1 plus x square plus x cubed plus and so on, which is an infinite GP, the sum of which is 1 by 1 minus x. Clearly thus S is 1 by 1 minus x whole square. Next question, find the answer. A similar problem, call the series S and write it. Multiply by 1 by 3 to get. Now subtract. The next step involves taking 2 common and we have an infinite GP series. This leads to S equal to 9 by 2, the answer. We now wind up our discussion with a few questions of multiple type. In fact, we have done the calculations already and it would be easy to answer the questions now. First question is, denote commutator of two matrices A and B by, and the anticommutator by. If the anticommutator is 0, then which is true for? The options are, and the answer is. Next question. The trace of the real matrix U equal to exponential A, where A is the matrix, is equal to, the options are, and the answer is. Next question. The value of the integral is, the options are, and the answer is. Next question. The probability function for a variable which assumes only positive values of f of x equal to x into e to the power minus x by lambda, where lambda is greater than 0. The ratio average x by xp, where this symbol is the mean value and xp is the most probable value of variable x, is. The options are, and the answer is. Next question. What is the value of x if log x plus 1 equal to log x plus 1? The options are, and the answer is. Next question. What is the value of 1 plus 4 by 5 plus 7 by 5 square plus 10 by 5 cube plus? The options are, and the answer is. Next question. What is the value of? The options are, and the answer is. We come to the next question. The sum of the infinite series, call it S, equal to. The options are, and the answer is. Next question. The sum of infinite series for mod x less than 1. The options are, and the answer is. Next question. The sum of infinite series. The options are, and the answer is.